said, all right, well, let's take a look at this. You know, we've got someone spending 10 to 15 hours on one of these. They're limited in size and the breeds of dogs you can work on, lower success rates, and really no repeatability. There's just one single person who has the ability to do this. And while there's a ton of need for this, it is just not feasible to spend time on this. And so we were like, okay, if we can hit these marks, then we might have the ability to create a better product that actually works and, you know, has a difference. And so the first thing we started with is, okay, how do we replace that 45-pound plaster mold? Because no matter what, you have to either cast the animal's torso and get a 3D scan of that, or you're going to 3D scan the mold itself. And we said, well, if we could program in the offset of the thickness of the mold, then we can get very close to an exact replica of the torso of the canine. So we took this old iPad, we took this structure scanner at the time. This was about 4 years ago. And this is really the only thing that you could use at the time. And we said, all right, we're getting pretty decent scans here. Let's see if we can do the offset. Let's do some manual work and see if we can create something on the computer that could represent one of the old harnesses. And so the next task was, okay, we've now taken that 45-pound mold and we've now just eliminated it because we're doing 3D scanning of the plaster, I'm sorry, of the cast mold. So instead of having to pour plaster of Paris, now we're just doing the cast mold. And that essentially replaces the need for us to thermoform plastic over that large mold. And so we developed a custom piece of software, and I'm making this sound very easy, but it was months and months of development to create a software that we could essentially bring this 3D scan of an animal into, pick out where the holes will be and where the cut lines and trim lines will be, where the breathability is going to be, where the structure is going to be, where the flexibility is going to be. And so there were a lot of metrics that had to go into the software to figure out what the output was going to be and how reliable that output could be, and if it could be repeatable. So once we had kind of gotten to a very preliminary version of this software that we could start to run some tests with, we moved on to the next stage, and that was, how do we eliminate the need for 3 layups of this plastic as well as the final carbon fiber or polypropylene layup? And that was 3D printing, which we had knowledge of because of the work that we were doing at the health design lab, as well as a lot of the prototypes that we've been building through our industrial design courses. And so we had reached out to a number of very large entities in 3D printing, multi-million-dollar companies who said, you can't print something of this complex geometry. You can't print something of this complex geometry that's flexible. You can't print flexibles this big. If you were to print flexible, basically doubt upon doubt upon doubt from these very large entities who had very expensive machines. And we kept looking at ourselves, and I think it was because we were a little bit naive, but we were also not ready to give up at this point. We said, how is it possible that this is not achievable? And so we started off with some very inexpensive machines, and we started running some very basic tests using materials that we had purchased just to test with, some polypropylene, some levels of ABSs. We've been taking recommendations from experts in the field at the time. And everyone was saying, stay away from flexible filament. It's not going to solve your problem. Well, that was quite the opposite. And when we finally came to that realization and started understanding how you can work with flexibles and how you can print with them very efficiently, we were really onto something. And so rather than having this very rigid 2-pound piece of plastic on an animal prior to any of the hardware being attached, we've now got our software designing a harness that can be flexible in very specific areas and rigid in others, like where the prosthetic leg is going to mount to, and so on. So now we're kind of like coming on to the full spectrum of how this product's going to come together. And we reminded ourselves where we started. So we've got 10 to 15 hours of labor, limited access, low success rates, and we're on the verge of transforming that down to a 2 to 3 hour labor process, a scalable solution, and something that is more tailored to the animals and more adjustable. And I'm really speeding up what was a very, very long process here, and I'm going to go into the details here, and we'll show some additional videos. But the whole idea of these prostheses is to reduce the amount of wear and tear on the remaining joints, preventing hyperextension, reducing the onset of arthritis. And I think we've done that in a lot of senses. We're working on laboratory tests now. We're actually doing gait analyses